Welcome to solverfy.
So here for part A, we can imagine dividing the one-turn solenoid into n small circular loops. We're going to then place those circular loops along the width of the copper strip. So we can then say each loop that we are essentially imagining here would be delta I equals I over n. So we can then find the magnetic field inside the solenoid and say that the B is going to be equal to the magnetic permeability in a vacuum times N times delta I, and this will equal the magnetic permeability in a vacuum multiplied by the number of loops divided by W multiplied by I divided by N, and essentially here N's cancel out. So we have 4 pi times 10 to the negative 7th. This would be the magnetic permeability in a vacuum, Tesla meters per amp, multiplied by the current of 0.035 amps, divided here by W, the width. And this would be 0.16 meters. Therefore, the magnitude of the magnetic field would be 2.7 times 10 to the negative 7th Teslas. This would be our answer for part A. For part B, to find the inductance, we simply use equation 3033. And so L would be equal to the magnitude of the magnetic flux divided by I. This would be equal to the area, pi r squared, times B, the magnitude of the magnetic field, divided by I. This is equaling pi r squared multiplied by the magnetic permeability in a vacuum times the current divided by W, the width, all over, again, I. And so this would be equal to the magnetic permeability, rather pi times the magnetic permeability in a vacuum, multiplied by r squared, divided by the width, W, given that, of course, the current here, I's, cancel out. At this point, we can solve. So the inductance would be pi times 4 pi times 10 to the negative 7th Tesla meters per ampere, multiplied by 0.018 meters, quantity squared, divided by the width of 0.16 meters. And we find that the inductance is going to be equal to 8.0 times 10 to the negative 9th henries. This would be our final answer for part B. That is the end of the solution. Thank you for watching.